I'll start with a short introduction to reinforcement learning for anybody that isn't so familiar with it. Then the problem definition that we're trying to solve, our simulation that we built, a few policies that we tested and we conducted, and then finally the robotic prototype, which we built in our lab. Yeah, sure. No problem. Now, can you see the full screen? Can you still see the notes?
That's great, Chana. Thank you.
Okay, sure. Okay, so reinforcement learning. If we look at it, the difference between reinforcement learning and supervised learning is that in supervised learning, we have labels and we use those labels for training. Whereas in reinforcement learning, it's actually based on a simulation and a reward function, which leads the policy to a better actions and better decisions. And if we see here on the left, we have apples and oranges, and supervised learning, we would differentiate between apples and oranges. Whereas in reinforcement learning, we usually try to do path planning or decision making, and we don't actually know what the right choice is, but we let the algorithm try to figure it out. Just a few terminologies that I'll be using throughout the talk. So an agent, that is actually our policy or what is trying to perform actions within our environment. The environment will return states and rewards, and the agent will actually use those to decide the next action. So now going to our specific task, here we can see a bulldozer on the left performing what we call the grading task. Just to understand how this works, we have a dumper, which actually dumps sand piles at the beginning. Then the bulldozer comes along and tries to actually raise this whole area by a certain height by flattening these sand piles, and that's what we will focus on. And finally, after us comes a compactor and actually fixes the area and creates a better area, a more flattened area and more smooth area. So if we think about the task is actually to recognize where sand piles are and then choose how to move over these sand piles to flatten the area. If we look here at a cycle kind of how we would do this, we would start with defining our scenarios. So we define scenarios for a real bulldozer to perform with all the sensors that we would put on the dozer finally in order to be autonomous. Then we collect this data. We generate height maps from this data. And actually the input to our model is a 2D image where the values are the height in each pixel. We use this real data to improve our simulator, which I'll talk about soon. And then using the simulation, we train our reinforcement learning agents or behavior cloning using the simulator and the heuristic. And then based on the results that we get, we can go back and define new scenarios to collect. What are we actually using? What are the components that we had to develop? So first we had to develop a heuristic. We had to develop some kind of baseline based on expert domain knowledge. Then we use that in order to train our AI agent. And soon I'll explain why you need AI, because some might think the heuristic is good enough. And then we actually have three different types of simulators or real world bulldozers that we can train or try our algorithm on. So we have our simulation, which is where we train the AI agent. We have a prototype, which we built in our lab, and we can run our trained agents on. And then we have the real world dozer, which is actually at the end where we would want to see that the algorithm works and is robust and gives us good results. So I'll talk about each one of these components now. So if we start, let's start from the simulation. What exactly is the simulator, why we need it, and how it works? Our simulation is actually in order to run the bulldozer. We define the problem in three different types of problems. We have an initial problem where there are just sand piles laid, and we need to flatten them and actually start to create this flattened area, which you can see here in the middle image. Then we have what we call a continuous problem, which is where a bulldozer has already flattened a certain area, and now we have to continue that flattened area and enlarge it. And finally, we have what we call an edge problem, which is where you already have a large continuous area, and now the idea is to finalize it and create kind of like a diagonal um, area. So we can see here on the right, we have different examples of scenarios that we created. These scenarios had different sizes of sand piles, different distances between them, and we were able to actually train our agent on a large variety of sand piles. And on the bottom, we can see here an example of a specific action within the simulator. We used a numeric simulator where in each step, we were actually able to move the sand mimicking a real bulldozer behavior. If we look here, we can see two types of actions. We have a movement action, which is where we tell the bulldozer to move forwards a certain distance. And we have a rotation action, which is where we tell the bulldozer to rotate a certain amount of degrees. These are what we would call the lowest level actions, and we use these in order to perform more high level actions, which are a combination of these. These actions are actually in body axis. And now if we talk about our heuristic, here we can see in the picture two examples of heuristics that we found in papers when we started looking into this topic. On the left, we can see what's called a side attack, where the bulldozer each time approaches the sand pile, but if you can see here, the blade is not full. And that way, every stroke actually removes the full amount of sand wanted. So it takes more strokes and it could take more time, but you only have to go over the pile once. On the right, we see what's called a middle attack, where the bulldozer attacks the sand pile, where the blade is full with sand each time. But due to spillage and other side effects, we actually notice that the bulldozer has to go back in the end and repeat its actions on the leftover sand in order to grade the whole area. Our heuristic is based on this knowledge, and what we did is we first detect sand piles. So given an image where the bulldozer and sand piles, we first detect what a sand pile is. Then we choose the nearest sand pile and create two lines around it. One with points that the bulldozer will drive to, and then another one with points defining where it will start its next action. Once these points are chosen, we then choose the actual point where the bulldozer will drive to, and then another point the bulldozer will reverse to. And if we think about it, that is a high level action space. And in order to break that down into lower level actions, as I described, the bulldozer, we call these points P and S. The bulldozer drives to point P and then reverses back, makes a small turn, and drives forwards to point S, as you can see in the video here on the right. So the bulldozer drives forwards, then backwards, and then starts an action again. And we call this algorithm the SNP algorithm, or our heuristic baseline. So now a little bit about the AI algorithms that we chose to do and how we chose to perform them. So the methodology that we used, as I said, is we had a real bulldozer. We used this real bulldozer and real data in order to create terrain maps or height maps, which are 2D images with pixel values in each image of the height of the terrain. Then we took what we got in the real data and created those in the simulation. So we were able to check and validate that our simulator was close enough to the real world. And then using this data in the simulator, we actually trained an agent, either with reinforcement learning or behavior cloning, which I will explain about soon. And we continued this loop only in the simulation. And once we had a trained agent, we could go back and test it on our prototype or on the real data and see what we were missing in our algorithm in order to then perform the task again. So this is kind of the loop that we performed many times. And if we dive a little bit into the algorithms, we actually looked at three types of RL algorithms. One is a pure online PPO algorithm where your agent interacts with the environment, and then the neural network is trained as the policy, and then we interact with the environment with the new policy. We get data, we train the agent, and so on and so forth, where we have a policy network and a value network, which I'll show the architecture of in a minute. We also have a type of training which is called behavior cloning. In this case, we have data collected by some kind of expert, and then we actually train the model with supervised learning methodologies on the expert. And then we can also go back and collect more data and use this export in order to train the model. We can see that in the future this works pretty well. And we had another type of model where we did what's called a hybrid model, where we would use the reward function in reinforcement learning and combine the reward that we got from the trained policy with the reward that we would get from an expert if it was reaching the same state and the same had to choose an action. So what exactly was the architecture of our model? As I said, we had a state. This is an example of a state where we see the bulldozer is here. The gray area is what we call the field of view of the bulldozer. In the real world, we don't have a full image of the whole area, but we have a limited image because there's limited sensor capabilities. This is what actually goes into the observation, which goes into the model. So the input to our model is what we call an observation. And this is the field of view of the bulldozer, and it's always in bulldozer body axis. And this is to allow generalization. Once we have that, we enter the model. We have a feature extraction model, which I will explain about soon. And the end of the feature extraction model is two heads. One is a policy network and one is a value network. And both of these are actually used afterwards for training the policy model, which is in the end what we use in order to choose actions. So if we look at our feature extractor, in order to do feature extraction, we didn't want to use supervised learning because it's very hard to recognize what is a sand pile. And therefore, we used some different types of unsupervised learning. We used the contrastive learning methodology, where actually this part of the model is trained on different images, similar to different papers in the past. We also tested different backbone networks. So we tested YOLO Light and ResNet. And in the end, the interesting thing was that actually fully convolutional networks worked the best because they maintained the sand pile kind of area. Another important thing that we used is downsampling, where we took the original observation and we downsampled it. And this, on the one hand, left the sand piles and still allowed us to recognize them, but also allowed for a much smaller network, which was able to train faster. And finally, we used Gaussian masking, where we said we know the actions the bulldozer would choose are around the bulldozer's location. So we took the final probability function that we got from the observation and we masked it with this Gaussian masking, saying that closer to the bulldozer actions are better than further away. If we look here, we can see three examples of results. On the left is what we call our heuristic. We can see here the trajectory that the bulldozer performs. I'll play that again. So you can see that the bulldozer kind of performs each sand pile at a time because of the way we define the heuristic, where each time it attacks the sand pile nearest to its location. In the middle, we can see the behavior cloning agent, which is trained on this SNP heuristic. So we can see that it mimics the heuristic very well. And on the right, we can see the reinforcement learning agent, which actually performs the task a bit differently, but also mimics the behavior of the SNP since it was a hybrid model. Finally, we see that the reinforcement learning agent manages to generalize on the heuristic, to mimic it on the one hand, but also choose actions that are further away and cover the sand piles in a faster approach. So you can see there are two rows of sand piles, and it manages to perform the grading task on both sand piles at the same time, whereas the SNP only chooses one at a time because that was the baseline defined. Now I'll talk a little bit about our prototype. So in order to actually test our model and make sure that it was working well, we had to build a prototype in our lab since testing it on a real bulldozer seemed not so responsible at first. So our prototype is built out of different components. The first component is the Uruku symbols you can see here on the ground, which we also have one on the bulldozer for localization and recognizing the map. The second component is the MEC camera, which is the depth camera to understand the height of each pixel of the terrain. We also had a robot, which we built, and I'll show more in depth in a minute, and sand piles, which we wanted to grade. The whole sandbox is about 3 meters by 3 meters, and it's about a 1:9 scale to the real problem. If we look at the robot that we built, we have control over the blade. We also have a computer which controls it and gives it actions to perform. And we have the batteries which help it move. So if we look here, this is just an example of how it works. Here we can see the RGB image on the left. In this image, we see the bulldozer and the 3 sand piles. This is already in what we would call God's view axis. So it's taken from the camera axis and projected onto the real world. Here we can see the observation. So the depth image performed from the camera in the real world, you can see that it looks very similar to what we have in our simulation. We have the bulldozer here on the bottom. This is its location and the 3 sand piles. And this gray area is what we call the observation or the field of view of the bulldozer. And here on the bottom, we can see already the algorithm planner on the real world data. So you can see the bulldozer is located here, and the algorithm recognized the sand pile and shows the green point as P and the red point as S. And here we can already see the planner, which given the green point, plans how to move towards it. So we can actually see the full algorithm performed on our real prototype. And if we look here, we can see a comparison between our simulation, where we do a continuous problem of 3 sand piles, and then after that, the same exact problem performed in real world data. So the bulldozer is performing the SNP algorithm. On the left is the RGB, and on the right is the depth image. I'll show that again, just in case somebody missed it. And we could see that they're very similar. So this gave us faith that our simulation was working well and mimicked enough of the reality in order to train the agent. It's important to note that the simulation doesn't have to be exactly like the reality, but has to be close enough in order to actually perform the task properly and then train an agent which would work in the real world. And if we look here, we can see a real video. This is live in real time of our prototype performing the grading task using a reinforcement learning algorithm, which was trained in the simulation. So we can see that the dozer moves forward. This is taken by a side camera just to for clarity. And now we can see that it will choose to reverse and go back, and then it will straighten out and go to choose the next action. Um, so this is basically our algorithm. So to summarize, we started out with a simulation and domain knowledge on how to build a heuristic. Once we understood the heuristic, we built an AI agent, which we trained using behavior cloning and reinforcement learning. And once we had a trained agent, we could use that agent to test it on our prototype. And finally, we could go back and define new data which needed to be collected in the real world, and then use that agent to on the real dozer and test it in the real world once it was working on our prototype. That's it. If there's any questions, finished a few minutes early.
That's very cool, Chana. Thank you. Would you like us to open it up to questions, or would you have some final remarks? Sure. Oh, perfect. Great. So the questions were coming in fast and furious as you were giving your presentation. So thank you very much. I'm going to go in just in the order that they came in. Did you need to calibrate the model to the physical world? If so, how did you fine-tune the control loop?
Okay, so if I understand the question, what we did is that we calibrated the simulation to the real world. At first, we built a simulation which was what I would call pure. It did not include all kinds of artifacts that we know exist in the real world. For example, the depth image was not as simple as you see in our simulation images. And then once we understood what we were missing, we could go back and test and add that to our simulation and see how it affected the agent. But the idea is the simulation does not have to be exactly the real world in order to work.
Okay, how do you deal with problems in the real world that you haven't simulated in the simulation? And they've listed examples, for example, a tree branch blocking the way.
Okay.
And sorry, pardon. And the second part of the question, in addition, is a model trained this way in general? I.e., can I use the model to flatten a different type of land?
Okay, so I'll start with the first question. Our assumption is that we're in a construction zone. And in a construction zone, from what we understand from different customers and from people we've spoken to, it is pretty easy at this point to define what we would call a sterile area. So an area where we don't expect to see humans or trees. We do have an object detection algorithm that was built by other people on our team, where given that it recognizes a human or a tree or something in the way, it automatically tells the bulldozer to stop. And then that object is removed and we continue. And if I approach the second question, yes, we can use our methodology on other terrains. The terrain type is a parameter in our training loop, so we can train on different terrains and then test our algorithm and see if it works. But I would imagine that you would have to retrain the model on the specific problem that you want with very simple tweaks. So that's your answer.
Okay, thank you. We have a third question from the audience. Does the model optimize the movement of the bulldozer? If so, how?
So I hope I understand, what the model optimizes is the final assignment. The reward function includes how much volume did you remove, did you reach the target surface, and how long the assignment took. And it does that by choosing the bulldozer's actions. So there isn't specifically perform this action versus that action, but more overall achieve the assignment.